Hi, this time I wrote a program that runs directly on the computer without an operating system. When you turn on the computer, the first thing that happens is it boots firmware on the motherboard called either BIOS or UEFI. These stand for Basic Input-Output System and Unified Extensible Firmware Interface, respectively. BIOS has been phased out for a while now, but we're going to talk about it here because I thought older hardware would be more simple to work with. I actually still don't know if that's true yet. These firmware programs' main function is to search for a piece of software on an attached device and load it directly into memory, at which point the software will load the main environment the computer uses to manage memory, programs, and user interfaces. This process is called booting, from the term bootstrapping, and the startup program is called a bootloader. The environment that gets loaded is called the operating system. In this case, the BIOS loads my program, which is a far stretch from being called an operating system, or even a bootloader, but it does mark the first step towards making one. At this level, a program really doesn't exist independently of the hardware, so you need the details about the system it's running on to really do anything. For my purposes, the computer architecture looks like an Intel i386 processor connected to PS2 serial ports for a mouse and keyboard, with VGA output for a display and a COM port for a serial port. We are also connected to up to 2 GB of RAM, I think, and a whole 1.4 megabytes of space for our program in the form of a floppy disk. The CPU interacts with most of these peripherals by addressing them on an I/O port through special I/O instructions. This system is running on a virtual machine using Qemu. Qemu has many options for architectures and peripherals, but I was emulating the Intel i386. The devices mentioned before are a few of many that are supported. The Intel i386 is in the family of processors that are the origin of the x86 instruction set. The first proper member was the 8086, which was succeeded by the 8186, then the 8286, then the 8386, known as the i386, the 8486, known as the i486, and the 8586, known as the Intel Pentium processor. I think at this point the naming for the family tree gets fuzzier, but modern x86-64 hardware is still roughly backwards compatible all the way back to the 16-bit 8086. For reference, the 8086 came out almost 50 years ago in 1978. This means that, theoretically, I think the program I wrote should be able to run on modern hardware, though I haven't tried. When we turn on this virtual system, it boots into an emulated x86 BIOS called cBIOS that attempts to find a boot sector on an attached device. In this case, it's checking the first sector of the virtual 1.4 megabyte floppy drive to see if it ends with a hexadecimal number 0xAA55. If it gets recognized as a boot sector, the BIOS will load the sector to the memory address 0x7C00 and run whatever code is located there. This boot sector is a whole 512 bytes of memory that we're free to write whatever program we want to, and with it we officially move from the virtual hardware space into the software space. The program I wrote is entirely written in assembly and operates with 16-bit instructions in the processor's real mode. This basically means the CPU is like a faster 8086 rather than really taking advantage of the i386 capabilities. Some of the main drawbacks of real mode are there is no memory protection to isolate different parts of the program, and memory is addressed directly with 20-bit addresses, meaning that we're limited to 1 megabyte total. We can fix these issues by switching to protected mode, but I don't do that. Also, it was only a couple days ago, but I don't really remember why I wrote it in assembly. I think I thought setting up a C environment sounded like too much work, and this would be more fun anyway. Again, there's a lot of hardware details that are important, so we'll briefly talk about some of the basics for what's essentially an 8086. The x86 architecture in this mode is made up of several 16-bit registers that store data and addresses. The main data registers are AX, BX, CX, and DX. They can be addressed as full 16-bit registers or split into two 8-bit registers that can be addressed individually. For example, AX can be split into AH for the A register's high 8 bits and AL for its low 8 bits. On top of these general registers, there's the SI, DI, SP, and BP registers. They are described as source, destination, stack pointer, and stack base pointer. So far, the SI register has been used in string reading operations, and I haven't used the DI register, but I believe it's used for string destination operations. The stack pointer is the reference for the top of the stack, and the base pointer is the bottom of the stack. There are other registers, but the last group I'll mention for now is the segment registers. The 16-bit x86 has memory addresses that are 20 bits wide and addressed by a segment register and an offset value. The address is found by shifting the segment register up by 4 bits and adding the offset value to the result. This memory addressing system means that the memory is grouped into 64 kilobyte segments that sit at addresses that are 16 bytes apart, meaning they overlap quite a bit. Each operation has a base segment register it uses for addressing, but some can be altered with different instructions. The segment registers are called code, data, stack, and extra. The code segment register is used to point to the segment for instructions and offset by the instruction pointer. Together they point to the memory address of the current instruction being executed. The stack segment register points to the segment containing the stack using the stack pointer as the offset. The data segment does the same for operations using variables and strings using the SI register. And lastly, the extra segment register is used for string destination operations with the DI register, but it is sometimes used for other operations as well. If you want more details, you should look into the programming manuals for the 8086, the i386, and the other x86 CPU family. I think just those first two are a combined total of 1,200 pages of information that should hopefully answer most of your questions. With that out of the way, we can look at the code. The first thing we need to do is set up the stack, or it could overwrite our code in memory. It seems to be advised that we disable the interrupts while doing this. We're still running in the BIOS, and I think the idea is the BIOS interrupts are triggering in the background, which will use stack operations, and we don't want that to happen in the middle of setting the stack pointers. We'll re-enable them when we're done. Now, the BIOS is standardized to load the boot sector to the address 0x7c00, so we need to let our program know that that's where we are. We need room for our stack to grow without eating our program, so we'll offset from the start address and add the size of the boot sector. We're updating the stack segment, so as mentioned earlier, we need to calculate the address of the segment it points to by dividing our address by 16. This is just undoing the 4-bit shift it uses to point to addresses. Alternatively, we can use the org keyword to set these offsets, and the assembler will add in offsets for these addresses automatically. We'll then set the address for the stack pointer, which I believe should just be the size of the stack in bytes. The stack pointer is the offset from the stack segment, and it decrements for every byte added to it. Once it reaches 0, it should meet at the segment location. We would really prefer that doesn't happen though. We also want to set our data segment to the correct address as well, so that our variables and strings are read correctly. Now, most functionality requires devices to be read, but the BIOS provides us shortcuts we can use for most of the basics. It's really meant to just give us some tools that ease the process of getting the operating system up and running, but we can cheat and use them for now. BIOS services are used by triggering software interrupts with the int instruction. The specific routine that gets triggered is selected by the AH register. In this program, we're using the video services interrupt to write a character to the screen. This is done by triggering interrupt hexadecimal 10, while AH is set to hexadecimal 0E. The routine reads the value stored in AL and draws the corresponding ASCII character to the screen. I would expect CBIOS to have a map of the interrupt vector table somewhere, but I ended up finding the programmer's guide for the Phoenix BIOS from Phoenix Technologies. Some of the specific details are vague, but it still has a lot more information than what you can find from many examples on the internet. I mentioned earlier that we have 512 bytes of space to run our code. Now, Not to be ungrateful, but we might have trouble fitting something like an operating system into that. We can use our program to load more code into memory to give us more room to work. Unfortunately, as we mentioned earlier, real mode only allows us to address 1 megabyte of RAM, and even worse, since we aren't a full-fledged operating system, we have to share it with the BIOS. There are also some blocks like video memory that are occupied by other hardware as well. To get started, we can choose a spot in the free memory, like just after the bootloader, and load our code there. But we also need to make sure our stack isn't assigned in a place that will eat through it either. When we're ready, we can call the BIOS interrupt hexadecimal 13 with AH set to hexadecimal 02. There are various register values we need to set to read the correct sector. Floppy disks are laid out in concentric circles called tracks. A sector represents a 512-byte arc of a track. A disk can be single-sided or dual-sided, so the read head can be selected to choose which side to read. I think the drive number is for readers with multiple disk slots. The boot sector is address 1, so we need to read address 2 and whatever other sectors we want into memory. I found it easier to start by reading a string from the beginning of the next sector to make sure that the sector is loading correctly. I ran into errors trying to jump to the next sector code in a different file because my segment registers were incorrectly set. Once you get it set up, you can start jumping to code in other sectors. With this newfound freedom, we can write some drivers for hardware. The OSDev wiki recommends a serial port, so I started there. The serial port connects to the CPU with an I/O port, and we can communicate with it using the in and out instructions. Ordinarily, you'd use the documentation to tell you the addresses and details, but that's not quite as simple for virtual hardware designed 20 to 30 years ago. Luckily, the serial port and the mouse and the keyboard are mostly standardized to specific port numbers and protocols. The base address for the COM port is hex 03F8. And there are several control registers that can read and write to it by adding an offset to this value. I really just found the initialization sequence on OSDev and converted it into assembly from C. Once it's set up, the wiki recommends testing it with a loopback test, which is a mode that allows us to send a byte to the device and it will echo it back to us. This lets us test the transmit and receive lines of the device. If it all works, we can send data to the COM port by using the out instruction followed by its port number and the data we want to send. We can receive the data in a similar way with the in instruction, the port number, and the register we want to receive the data to. The other end of this virtual cable is configured using the -serial flag when running Qemu. We have several options to choose from, but I was either using the standard I/O to send it to the terminal or a file name to store it to a file. I believe you can split the output to multiple targets as well. I guess the last thing to talk about is the build environment for the code. I was using NASM, or NSM, or however you say it, as an assembler, and DD to build the floppy image. I'm not actually sure if these are Linux-only tools. You might need to find other methods for other operating systems. I would build the files as binaries using NASM, create a 1.4 megabyte disk image using DD, and then run it as a floppy device in Qemu. The disk image can be created using DD and filling it with 2,880 512-byte blocks of zeros using /dev/0. Then DD can be used again to write the boot sector to the first block of the image, but you have to add no trunc to not truncate the data from the rest of the image. The boot image has a FAT12 descriptor, but I'm not fully sure what this does yet. I'm not really using a file system, I'm just concatenating my other assembly files to the end of the boot sector and reading them directly from memory. Remember to set the last 2 bytes of your boot sector to hexadecimal AA55. If you don't, the BIOS won't be able to register it as bootable. The result can be fed into Qemu and it should run it. That's most of what I learned from this project at this point, and I'm going to have to call it here. That's enough to emulate a system, boot from the drive, read code into memory, use the BIOS interrupt to communicate with peripherals, and directly communicate with the terminal using COM ports. If you have the means to and are interested in supporting these projects, I have a Patreon in the description. This really does help me continue making these videos, and I would like to continue making the content available for free if I can. You can think of this more like a tip jar, since I don't have much to offer supporters right now other than my sincere thanks. Maybe I should describe it more as crowdfunding the videos so they can be made and released to everyone. Thank you for watching. I hope to see you in the next one.